Alright, so my horizontal axis will be in t, which is s, and then up here will be force, applied force, which will be in newtons. I'll scale this with 0, 1, 2, 3, 4, 5, then 100, 80, going down, 60, 40, 20. So we can see the points here: 0, 100, 1 to 80, 2 to 60, 3 to 40, 4 to 20, and then 5 to 0. Then we can draw a straight line to connect them, and this should be our line, which will give us a straight line. Okay, so for part A, we're going to label this axis right here, the horizontal, as t for time, and the unit is in seconds, and the vertical is going to be force, which here will be the horizontal force that's exerted, and we'll label that n. So the force on top here, the force here goes from 100 to 0 in increments of 20. So 100 newtons, 80 newtons, 60, 40, 20, and then 0. And then this starts at 0, then it goes to 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. Then we can start graphing it. So it's 0, 100, 180, 2 to 60, 3, 40, 4 and 20, and then 5 and 0. And if we draw a straight line going through this, it goes from here, and then it goes down. What we notice is that this is a perfectly linear line in this case. So this goes on to part B, which I'll write over here. So 2B, so f of t in this case, we can model off of this right here. So f of t is equal to, so we need our change in t, so I'll write the slope as m, and our unit is time, plus the initial force. So what we notice here is, so I'll write f of t again. So it goes from 100, as we see here, it goes from 100 newtons to 0 in 5 seconds. So I could write the change in force is 0, is from 0, which is final, minus 100, over 5, which is the time it takes, minus 0, which is where it starts, t, plus our initial force applied is 100. And then if we simplify this simplifies down to negative 20 t plus 100. And this will be our f of t. Next up, for 2c, we're asked for the acceleration. So we could write f of t is equal to m a of t. Because in force equals mass times acceleration. And then I could rewrite f of t here as negative 20t plus 100, which we got from part B. And then our m, which is we were given as 5 kilograms, and let's multiply a of t. We could divide by 5 both sides to get negative 4 t plus 20 is equal to a of t. And this unit will be in meters per second squared. This one will be newtons, because the unit for force is newtons, and this one is for acceleration, it's meters per second squared. And then we go back over here. So for part D, I'm going to label my vertical as time in seconds, my horizontal as time in seconds, and my vertical as acceleration, which is meters per second squared. So for my points, so I'm just going to label it before 0, 1, 2, 3, 4, 5. And now I'm going to divide all these values I got from earlier by 5. So this becomes 4. Then it becomes 8. And then 12, 16, and then finally 20. And we can regraph this. And if the way we scale it, it should look similar to the previous one. So we draw it. And this will be my linear function. As we see, it's similar to the other one. What we can extract is, first off, the change in acceleration, which we saw from our equation earlier, right here, is -4. And that means our jerk is equal to -4 meters per second squared. Next up, we could find our initial acceleration, which in this case is 20. So A0 is equal to 20 meters per second squared. This should be a cube, my bad. And then we could also find the change in velocity by finding the area underneath this linear graph. So we know its rise up, it goes down 20, and it goes across by 5 over 2 because it's a triangle. And what we get from this is a change in velocity, which is 50 meters per second. So our change in velocity is equal to 50 meters per second. Also, we can tell from this being a straight line instead of parabola, that our jerk will just be a constant jerk. So we'll have a constant jerk of -4 meters per second cubed. For the next part, for v of t function, we know v of t in this case would be equal to the integral of a of t dt. And once we get that, we could plug it in. So v of t is equal to the antiderivative of -4t plus 20 dt. If we integrate that, we should get -2t squared plus 20t plus v of 0, which are initial, but we can safely assume that in this scenario it's going to be at rest initially. So then my v of t function will be -2t squared plus 20t. And then for 2g, we're finding v at t equals 5. So all we have to do is just plug it into here. So -2 times 5 squared plus 20 times 5. And when we do that, it's -2, 25, -50 plus 100, which would just be 50 meters per second. Okay, for 2g, what we determined earlier from this is that the change in velocity is 50 meters per second. So change velocity is equal to 50 meters per second. And now, if we're trying to find v of 5, t equals 5, we would take the change of velocity from t equals 0 to 5 plus v of 0. Since we say v of 0 is equal to just 0 meters per second, we can say v of t equals 5 is just equal to 50 meters per second. 2h, we know that we're trying to use the v of t function here. So we're trying to find t equals 5. So we have v of t equals 5 is equal to -2 times 5 squared plus 20 times 5. And if we simplify this, it will come out 50 meters per second, which is the same as our previous one right here. For 2i, we're trying to find x of t. And now we know x of t can be found by anti-deriving v of t. So if we plug in v of t here, so v of t is -2t squared plus 20t dt, then we find x of t is equal to -2t cubed over 3 plus 10t squared plus xi, which we can assume in this scenario it's at 0. So now our x of t function is just -2t cubed over 3 plus 10t squared. Okay, for the next part, we're gonna graph x of t here. So I'm gonna label this axis right here on top as x in the unit of meters, and then my horizontal will be t, which should in the unit of s. So we go from 0 to 5, so 0, 1, 2, 3, 4, and 5. Now this one's a bit bigger, so I'm gonna put it as in increments of 40. So 40, 80, 120, 160, and 200. So now I'm gonna start graphing it. So my y1 is x of t already. So I'm just gonna check each value of the point. So the initial is 0. And the first one is at 9.33. So I could put it safely around here-ish. Then it goes to, at 2, it's at 34, so it's about here. Right here. Then I could do 3, which is 72. So I could put it right below the 80. And then 4, 117. So I could put it right below the 120. And then finally, 5, it's at 166, 167. So I could put it about right above this 160 right here. And if we draw this, this is what our graph will look like from 0 to 5 x of t. See that the S average as it approaches 5, it still increases, but the rate that it increases is decreasing. And if we compare the S averages to them and see how much they change, we notice that every second, the change in the S average is going down by about 1.33. And then for the final one, the average velocity, we could find that by doing V average from t equals 1 to 3 is equal to the change in position, so x of 3 minus x of 1 over the change in time, 3 minus 1. And we know our x of 3 in this scenario was originally 72 minus our first one was 9.33 all over 2. And if you simplify, you get about 31.33 meters per second. And in this scenario, it will be going in the positive direction, or where the line of motion would be currently right now.